we'll get started then. So this piece of work is a collaboration between the DiRAC National HPC facility, which is the HPC facility for particle physics and astronomy, and Oracle, who provided their cloud resources, and particularly we're looking at the Oracle Cloud Infrastructure, OCI, for use for DiRAC HPC work. I'm involved because as well as my roles at EPCC, I'm the DiRAC Technical Manager, and I look after the DiRAC RSE team as part of that. Before I actually get started with the content of the presentation, I want to mention the people who actually did the work, with the DiRAC RSE team, the Research Software Engineering team, and the Oracle HPC team. So the DiRAC RSEs who did the majority of the work on Michael Burford, who's a colleague of mine at EPCC at the University of Edinburgh, Alexei Borisov, who also works at the University of Edinburgh in the School of Physics and Astronomy, Arjun Tamaras, who works at the RSE team down at the University of Cambridge. On the Oracle side, Andy, Stuart, and Arno, who all provided useful inputs and contributions. Actually, I think the majority of the technical legwork fell to Andy. He was certainly the person who had to put up with our cries and pleas for help when we didn't understand things or things went wrong. He did all the setting up of the clusters in the Oracle Cloud for us. I'd also like to thank Oracle for arranging access to resources, and particularly Paul Morrissey, who did all the legwork on the Oracle side to get all the access sorted out and kept it going and made sure we had access to the different sizes of clusters as we went through the work. And before I start on the technical information talk, I just wanted to say a bit about motivation as well. The use of commercial cloud by academic researchers has been growing for a long time, and commercial cloud is heavily used by academia at the moment, but less so for HPC workloads. That's typically been for a number of different reasons, some of them technical and some not so technical. In terms of technical reasons, one of the problems has been, until recently, I think, that it's been difficult to get performance from the interconnect in the commercial cloud to support multi-node HPC jobs where you need the low latency, high bandwidth, MPI-like support between the nodes. I mean, there's a lot of offerings in commercial cloud for those sort of things, but I think until the last year or so, probably they haven't performed as well as people have needed to actually run these type of codes. So one of the things we wanted to evaluate in this project was how well that worked for DiRAC workloads in the Oracle Cloud Infrastructure, because they have a particular setup that I'll talk more about that had the potential to provide this level of performance required. On the slightly less technical side, there's also been challenges with usability for coming from traditional HPC into cloud offerings. So the use model of traditional HPC, although many would argue is not simple, I think that's true. There is a large barrier to entry for traditional HPC. You've got to learn command line, SSH, how to use a batch scheduling system, all these sorts of things. But most of the people who are using DiRAC resources are actually pretty comfortable with all of those aspects of using HPC and have spent time, invested time in learning those skills. The challenge when they go into offerings is that often cloud resources don't sort of look the same. Although you can get command line access, there's a lot of setup that has to be done in a web interface, at least initially. And then once you've logged on, sometimes you don't have schedulers and other bits of software, and we'll talk a bit about that throughout this presentation as well. So we wanted to assess how what the usability barrier might be for DiRAC researchers who wanted to use the Oracle Cloud Infrastructure for HPC workloads. And finally, there's also been a barrier in terms of cost. Often the instances that you need to do HPC are high-powered ones, which are scarcer in the cloud, so more expensive for that reason, and hard to get on some sort of spot price regime as well. And also you have to factor in the fact that you may need some high performance storage. You also have to have the nodes that have the particular interconnect to support HPC work. And all these things add up to make it quite expensive often to use these sorts of resources in the cloud. And as well as the expense, traditionally it's been quite difficult to charge, to try to get the charging model to work with academic resources, how to charge without just paying on a personal credit card. These are still challenging aspects of using commercial cloud within academic research, especially when the costs are going to be higher. Most people take a risk when the spot price is low for standard instances, but when you start using HPC instances, the costs can rocket quite quickly, and people are less likely to just have a go with their credit card, see how things work. Okay, so for the rest of this presentation, I'm going to talk briefly about the DiRAC application benchmarks, which we use to run the tests. I'll talk a bit about the cloud infrastructure that we use that was provided by Oracle, and then I'll present some results, both in terms of usability and performance in the cloud, before summing up at the end. So the DiRAC benchmark suite itself. So this is an application-based benchmarking suite at the moment. It consists of a number of applications chosen in consultation with the DiRAC community to cover the range of science and application type that the DiRAC community typically undertake. For those who aren't familiar with DiRAC, unlike ARCHER or ARCHER2, where there's a single large resource for the national service that everybody uses, DiRAC is made up of a number of different HPC systems tailored to the different requirements for different parts of the community. And these are known in DiRAC as extreme scaling, memory intensive, and data intensive. Extreme scaling consists of one system hosted up here in Edinburgh in the EPCC data center at the ACF. It's designed primarily for quantum chromodynamics type research, and for applications that scale to very large core counts to run. So the system's very large. It has actually quite low numbers of core counts per node, but a very powerful interconnect which matches the balance required for QCD calculations. The application benchmark for this system and for this science is called GRID, which is written by Peter Boyle, formerly of the University of Edinburgh, essentially a data parallel C++ library for QCD modeling. The memory intensive system, which is housed at the University of Durham, is primarily used for large scale cosmological modeling. Some people from that area may know of the Virgo Consortium and the Eagle runs. They were done with essentially precursors to the system at Durham and the type of work that Durham undertakes, and that group undertakes. The code in the application benchmark set for that site is called Swift, which is the sort of up-and-coming replacement for Gadget, which has been widely used for this cosmological modeling for a large amount of time now, but is gradually being replaced at the moment by Swift, certainly for the work that the DiRAC researchers are doing. The data-intensive systems, or the more general-purpose HPC systems, there's two of them, one based at the University of Leicester and one based at the University of Cambridge, and they have various different architectures, some which are standard sort of Xeon clusters with InfiniBand interconnects, some large memory capability, GPU capability, and some KNL capability as well. And there's a few different codes here, most of them astrophysics, AREPO, RAMSES, and SPHNG are or essentially astrophysics codes that are used by different sections of the community, and actually most of them are used by lots of different research groups. And there's also the TROVE application from the group at the University College London, which is used for molecular row vibrational spectra, for modeling molecular row vibrational spectra. And this helps with things like understanding the composition of exoplanet atmospheres and cool stars composition as well. So that's quite a diverse range of applications. They actually cover also a diverse range of models in terms of MPI plus OpenMP and the balance between processes and threads, and cover a range of compilers as well. So the C++ is covered there, Fortran and C in these all of these application benchmarks. So they do exercise quite a lot of different patterns of communication, a lot of different compiler features, and different types of parallelism as well. So they're quite a broad set of things. In terms of I'll move on to look at the Oracle Cloud now. In terms of the Oracle Cloud, the setup we had was that each node was one of these HPC instances. Each compute node, sorry, is one of these HPC instances, which consist of a high-end Skylake Gold processor with quite a high clock count, large amounts of, or sort of pretty standard amount of RAM for a HPC system. They also, which is unlike our on-premises HPC systems, have quite a large amount of local solid-state storage associated with each compute node. And that's not typical of certainly the HPC facilities we run at DiRAC. The interconnect is based over the Mellanox Codex X5 network interface cards with RDMA over Converged Internet, or ROCE, as known. So this is not what is typically used in HPC at the moment, which is InfiniBand. It's an Ethernet technology as well, though actually I can see more Ethernet technology coming, because the new ARCHER2 system, which is coming from Cray sometime soon, which I gave a presentation on last week, it also has an Ethernet-based interconnect scaling to up to 5,000 nodes. So certainly Ethernet is an up-and-coming thing in HPC interconnects anyway, as a competitor to the sort of more traditional InfiniBand and other proprietary Cray networks that have existed before. There was a shared NFS mount storage where we could put things like binaries, libraries, all the bits and pieces we need to make the codes run. That wasn't obviously a high-performance storage solution, but we'll talk a bit more about parallel I/O performance later on in the presentation. All of the benchmarks, with the exception of one I mentioned right at the end, were essentially compute only. They didn't have any dependency on parallel I/O. So we were testing the performance of the compute nodes themselves, the scaling and the interconnect, but not the parallel I/O subsystem. Okay. The nodes all run Oracle Linux, which is based on Red Hat Enterprise Linux, and came with GCC compilers and OpenMPI installed with the OpenMPI configured for the Ethernet, for the ROCE interconnect. So here's a little picture that shows a schematic of how the system worked. There's only 2 compute nodes shown in this picture, so it's not exactly totally correct. We logged in through a Bastion node, and then actually SSH directly to the compute nodes to run jobs and compile and work in that way. So I'll talk about the porting experience, the usability experience a bit here as well on the Oracle Cloud. So there are a number of differences from standard HPC systems, which would have been potentially a bit unfamiliar to sort of standard HPC. I mean, I'm certainly an old-fashioned HPC person, and it was definitely a different paradigm from what I was used to. So there were no software modules. The user account that we had root access, and we all the people working on the project share the same login account. We need to manage a lot of the software installations ourselves, particularly even things like compilers and system level stuff. The system came with an old version of the sort of system standard GCC, which, if anybody familiar with Red Hat Linux, is a very old version of GCC. It was GCC 4.8.5, I think. And the OpenMPI library that was on the images by default was compiled against this old version of GCC. Now, that was sort of fine and didn't cause a problem. We could install newer GCCs by using sudo yum install or something, and that all worked fine, but it caused a problem for the Fortran codes because the MPI interface is a Fortran module file, and different Fortran module files are incompatible between major versions in GCC. Okay, so the standard OpenMPI that was installed on the system work of the newer versions of gFortran for the Fortran codes. So that meant we need to go and recompile OpenMPI against the new GCC, that was fine. We got the instructions from Oracle about how they built OpenMPI in a suitable manner for the Mellanox high bandwidth Ethernet cards. We did that as well. Because there was no scheduler, there were sets of scripts on the system that Oracle provided for launching your MPI jobs, which essentially built up the correct host files, put together the right MPI exec command for you, and all those sort of things. When we recompiled against the new MPI, we need to go and have a look at them and work out how to modify them. It was pretty simple, but there were just a few steps that were probably standard DiRAC users, if such a thing exists, would have been less comfortable with. And actually, with a small amount of work on the HPC images that were provided, or the way things are set up, then actually a lot of those barriers could be taken away. So, but I'll mention that a bit more when I summarize at the end about how things could be fixed, or what things could be done there. I'm sorry, or maybe I'll mention it here actually. So but once we've got all those bits in place, the porting was straightforward. There was nothing different from a standard HPC system. You logged in, you had command line access, you make install whatever the piece of software you're compiling used. We needed to install some dependencies and things like BLAS, LAPACK, and FFTW. The ones we installed, we pulled actually from the sort of standard Red Hat repos in binary form, so they're probably not optimal for the system. The reason for that was just in terms of expediency of getting things running. What we wanted to test here actually was not that in some sense we could get optimal performance, but that we could actually get to the stage of porting things, compiling them, running them, and that the performance was reasonable or in line with a normal HPC system. Optimizing, working on optimizing the performance could wait for later, or was not the priority at the start of this task. So there's probably quite a bit of performance left on the table here, but that wasn't particularly the goal here. For some of the codes as well, it's known that there's a reasonably large difference between the performance of compiling GCC and compiling the Intel compilers, and the Intel compilers weren't available on the Oracle infrastructure. These are all things that could obviously be fixed with a bit of work, but as I've said, we wanted to get through the porting as quickly as possible to evaluate the performance, and then maybe if there's time, go back and have a look at optimizing performance. Okay, so porting was pretty straightforward, but we needed to do some bits that were probably unfamiliar to most users. In terms of running, a small amount of work on the scripts and the way it works could be made. It could be made much more user-friendly, and having an updated HPC image with a bit more built in would be useful addition. For example, newer compilers, some standard optimized numerical libraries, improved scripts for running MPI jobs will all make a very big difference in a short space of time. Now, the bit that we didn't do that Oracle did here was that they did all the setup in the OCI web interface for us, setting up the virtual network, the networking, and make sure that we had the right sorts of nodes and that they were all working together and things like that. So that will probably potentially be a bit of a barrier as well. But there is actually quite a lot of work going on to try and address this. So I know that Bristol have a tool called Clustering the Cloud that tries to automate the setup for you. At the moment, I don't think it's compatible with the bare metal cloud instances that we were using in Oracle here, but again, there are things that could be fixed. Yeah, thanks, Chris, for putting the link in. The Oracle Cloud is all compatible with Terraform and these sort of cross-platform tools. So actually, although I said it was probably a bit of a barrier for us, with a little bit of work from RSEs, with some help from Oracle, probably getting it to an automated state or having something that could work well, I don't think is a big problem there. So a small amount of work could have a big difference in terms of usability here, I think. In terms of benchmarks and what we've done to run them, one of the benchmarks was SVHNG. We never managed to get that working on the cloud infrastructure, but that's not a factor. That's not due to the cloud stuff itself. Actually, we've had some problems getting SVHNG to work on different platforms. It's been by far the most difficult code in the benchmark set to port. across systems. So this is not an Oracle or a cloud specific issue. It is the fact that the compiling this code and making this code work is actually quite fragile compared to the other benchmark codes and needs a bit more tweaking and playing with expertise to get up and running. So we're looking at that a bit more as well. So I'm going to go on and look at performance. Most of the performance data I got, as I've said, is for the applications running without any dependency on parallel I/O. So I do have one slide on looking at performance of parallel I/O for the Swift code right at the end of the performance data. There's quite a lot of graphs here. I'm probably going to go reasonably fast, but we'll put as I say, there'll be a recording here, and also we'll put the slides up and make them available to people afterwards so they can have a look at the data in more detail if they want. We also plan to publish a blog post on this work and a technical report as well. So there'll be more data available and more in-depth analysis available in the future as well. But what I wanted to do was put all the graphs in so you could see what the range of performance looked like for the different applications across the system. I should also say that we don't actually have all the performance data for all our on-premises systems yet either for the benchmarks. We're still working on that. So not all benchmarks have been run on all systems. So I've compared to all sizes. So I've compared what I can compare at the moment. But this is still work in progress. Okay. So here's a summary of the different systems we mentioned. So at the bottom, there's the Oracle Cloud system we've already talked about. There's the 4 DiRAC systems at the moment: Extreme Scaling, which is also known as Tesseract in Edinburgh, which has Skylake Silver processors. These are lower floating point performance processors. It has a lower amount of memory, only 96 gig RAM per node. That's why when you come to see the benchmarks, a lot of them don't go down to low node counts on Extreme Scaling because there's not enough memory available for some of the benchmarks low node counts. Its interconnects are very powerful, though. It's dual rail Intel OPA. It's optimized for the balance between interconnect performance and floating point performance that matches what the QCD calculations of the systems primarily used for need. There's the memory intensive system in Durham, which again has slightly lower it's got the Intel Skylake Gold processors, but they're the 5 series rather than the 6 series, which means they have lower core counts, and I think they only have one of the floating point units enabled instead of 2 per core. They have a large amount of memory per node, but again, I've underpopulated the memory banks, so they're not using all the memory channels, but they have got lots of memory. They've got a pretty standard InfiniBand interconnect. It's optimized for memory capacity as required by the cosmology simulation, the large-scale cosmology simulations or models that run on this facility. The 2 more general-purpose HPC facilities in DiRAC are the 2 data-intensive ones. The ones that are included here, because we haven't looked at really GPU performance or KNL performance here, are the 2 CPU-based systems, Petaflow Skylake in Cambridge and data-intensive at Leicester. Both of them have Skylake Gold 60 series with slightly higher core counts. They've both got sort of more standard amounts of RAM than the other 2 systems available, and both of them have pretty standard HPC interconnects, either Intel OPA single rail or Mellanox EDR. And the Oracle Cloud has probably the most powerful processors in terms of floating point performance on here, standard amount of memory, and has the Ethernet-based interconnect instead of InfiniBand, which is used for all the other systems. So let's start out looking at the grid, which, if you remember, was the QCD benchmark. And this is a weak scaling benchmark. Okay, so we should see the performance stabilize, hopefully, and carry on as the system as we move out in core counts. As you can see, we're only going up. In all cases, we'll go up to 32 nodes maximum size, because that was the largest cluster in the cloud we could get access to from Oracle at this time. And I'll mention a bit more about that at the end as well. So here we can see at the very top in the orange is the extreme scaling on-premises system performance. Sorry, I should also say that in all of these plots, up on the y-axis is better performance. So the higher the points, the better the performance. Okay, so the Tesseract system is the best performing. This is unsurprising, as is exactly what this system was designed to do, and it's about the balance between the interconnect performance to the compute power. Most standard HPC systems actually have too much compute per node compared to interconnect for these sort of calculations. So in terms to be able to spend the money efficiently for the extreme scaling service, they tune down the compute nodes, so you had more money to pay for extra interconnect performance to receive the balance you wanted. And you can see actually that the other on-premises system we run on is the dark blue line, which is the Durham system, Cosmos 7, which seems to give very poor performance, which we don't understand yet. So we're looking at that in more detail to try and understand why it's so poor. But the cloud performance is pretty much in line with actually a standard InfiniBand HPC system here. The difference between that and Tesseract is pretty much what you'd see between Tesseract and another on-premises HPC system. So actually, it's doing okay. There's a slight oddity in the performance increase from 1 node to 2 nodes, which we don't on the cloud, which you don't understand yet. But generally, it sort of looks as you'd expect for different systems. Gives us some confidence, actually, that it gave us the confidence that the HPC in the cloud was working as expected. The interconnect's working properly, and it looks like a normal HPC system. Move on to the next one. Similarly for AREPO, which is one of the astrophysics codes used for various different things within DIRAC, the performance seems to be at least broadly linked to floating point performance, because Tesseract, which has the worst floating point performance of all the systems, has the lowest performance here. There's only 2 data points for Tesseract in orange. But it's not quite, it's a bit more complicated than that, because actually the dark blue line, which is the Cosmos system in Durham, doesn't have the most powerful floating point performance on its processors, and the cloud system, the Oracle system, which has the most performant processors, is the same as Cosmos 7. So it's a bit more complicated than floating point performance. But again, the take-home story is almost nothing interesting to see here, right? I mean, performance looks very similar to standard typical traditional HPC clusters. So it's all looking fine here. You know, it's behaving as a normal HPC system would. Move on to RAMSES, which is another astrophysics application from data intensive. Here again, is a little bit different. The performance of scaling seems more complex than for some of the other benchmarks, because it doesn't seem to match floating point or interconnect or memory bandwidth in any reasonable way, or in any sort of simple way anyway. But again, okay, so the cloud is not doing as well as the on-premises systems here. But remember, I also said that some of the performance would have been left on the table on the cloud, because we haven't worked to optimize the performance at all here. You know, there's we're not using probably optical compilers or optical numerical libraries. So we could go back and look at optimizing performance and look at the difference. But at this stage, the interest is not in the details of difference performance. It's that the performance for the cloud for these HPC workloads is in the right place for a sort of standard HPC system. Okay, and in some cases it's doing better, in some cases it's doing worse. But in all these cases we've seen so far, it looks similar to AN or the HPC system that you'd normally see. We carry on, we look at TROVE, which is the row vibrational spectra, the molecular line structure modeling code. This one's a bit different. So the scaling seems to change, seems to tail off on the cloud system, which is the pale blue line in the middle, sort of similarly to Tesseract. Again, the Cosmos 7 system has some poor performance we don't understand, and the Leicester data intensive system does very, very well here. But up to 8 nodes, certainly, you know, the difference between the Leicester system and the cloud system is likely due to the lack of optimized numerical libraries, a slightly different compiler changes and things like that. After that, the scaling changes a bit. So we may be able to look a bit harder at that. But again, there are some differences here, but it's in the range of typical HPC system. And you're just looking at what the challenges are for different HPC systems rather than thinking, okay, the cloud is very, very different. Something's very, very wrong here, which is what the experience has been sometimes in the past. I've just got a couple more of these to look at. So Swift is the cosmological code. Here, this is what this is the code that the Cosmos 7 system was designed specifically to work with. So it does really well. It does quite well. Just potentially unsurprising as this was co-designed along with this code. The Cambridge data intensive system does very well as well, actually a bit better than the Cosmos 7 system. And the Oracle bare metal cloud is a bit lower here. Now, this is one of the codes where is known to be a big difference in performance between the Intel compilers and GCC, and dependency on the numerical libraries. So certainly up to 16 nodes, I think, and I argued previously in my talk that this difference is probably just due to the difference in lack of optimized compilers and libraries on the cloud nodes. And I think that's definitely true. There is something different going on with the scaling further out here, and whether that's just because the performance dies even more, so turnover, or whether it's actually something that's going on in the internet, we don't understand yet. But again, this is, to a first approximation, it looks like a tuning problem rather than a fundamental problem in terms of performance. Finally, I finally want to talk about the Swift I/O benchmarking as well. So I mentioned that we had done that none of these were really I/O dependent. We did, towards the end of the trial, have a look at parallel I/O performance in the cloud. Oracle provided us with a BGFS installation over the ROC interconnect using the local NVMe storage on the nodes. Okay, so they built a parallel file system that used the local storage with BGFS running over the interconnect. Excuse me, which is similar in spirit to what happens in on-premises HPC, where you have some parallel file system. It's delivered over the interconnect, InfiniBand usually. The difference being that usually the storage is all in one appliance somewhere rather than local to the nodes. Okay, so there are some differences here. So Cosmos 7, which is the Durham system, has an NVMe-based storage solution delivered over EDR based on Lustre. And we compare that to the BGFS we had on the cloud infrastructure. And actually, the cloud stuff performed really well. For the smaller files, which are the snapshot files, it gave roughly the same performance as the on-premises system. And for the larger restart files, it did a lot better in terms of performance. I have no more analysis at the moment about why these differences exist. Just to note that the parallel file system using MPI/IO, the standard sort of HPC way of doing parallel I/O, seemed to work quite well on the cloud infrastructure once the BGFS stuff had all been configured over ROCE. And that was, I guess, a pleasant surprise in many ways. My final plot is not a direct benchmark at all, because I managed to sneak in CASTEF, which is a benchmark I've run on a lot of different systems, not from the DiRAC side, but from the more Archer and Tier 2 HPC side. And so we'll have a lot of data from a lot of different systems of CASTEF. CASTEF is also relatively notorious for putting a high amount of load on the interconnect as you scale up, as it becomes dependent on all-to-all V calculations. So at low core counts, it tends to be floating point or memory bandwidth and memory performance bound, because it's generally tied up in LAPAC ZGEM. But as you scale up, the MPI latency starts to hit you, because you get bound in O2 or V for the parallel 3D FFT calculations. So it's a real test of latency of networks as you scale up. And here we can see that for the on-premises systems I have here, both Tesseract and the Cambridge Skylake system, the scaling is fine. By the time you get beyond 16 nodes on the Cambridge system, the performance is starting to turn over because of this balance between interconnect performance and compute performance. Whereas Tesseract, initially the performance is much lower because it's not got as much compute performance, but as you scale up, the fact that it's got the more powerful interconnect starts to have an effect here, and means it can extend its scaling. So the combination of low compute and high performance interconnect allows it to carry on scaling a bit higher. For the Oracle Cloud, the scaling turns over much earlier. The performance difference at low node counts is probably due to, again, lack of optimized numerical optimized LAPAC compared to the other systems. But then as the performance turns out, looks like there's maybe potentially some issues with latency on the interconnect, or with the way that the AutoV algorithm is implemented within OpenMPI on the Ethernet interconnect, which might have different properties for the tuning that's been done for InfiniBand. So there could be some tuning issues there as well, but it's a bit more complicated for CASTEF. Okay, so that's all the performance results I have, and I hope what I wanted to show you was that there's a variety of different performance, but actually the cloud system seems to be behaving as a normal HPC system, at least up to the node counts that we had access to as part of this trial. In terms of next steps, well, there's publications of the benchmarking report, publishing the DiRAC benchmark repositories themselves, so that other people can use them and build on them and use those benchmarks to investigate performance elsewhere. The idea here is that we include the benchmarks themselves, the information on how we compile them, our job submission scripts, the full output from our benchmark runs where that's possible. Some of the outputs are very large, it makes it very difficult to put it in a repository. And the analysis to scripts to show that how we turn the raw data into the performance that we saw. The idea here is that everybody can see all of our steps, which aids reproducibility. I've been doing benchmarking for quite a while now, and one of the things that really, really annoys me is you find some really useful benchmark results on a different system you want to compare to, and you look and all you can get is like a PNG of the graph or something like that. There's no way to actually compare the numerical data. So we're trying to avoid that here and trying to provide all the numerics and show all the steps we've taken, so you understand, so that people looking at the data can understand what we've done and reuse it and replicate it and compare to it. We've done some benchmarking on AMD Rome processors as well, which we would like to publish. We just need to get some agreement from people to be able to do that. Talk to other cloud providers to benchmark on their HPC offerings, because these things have changed so quickly over time as we've gone. The technology has changed hugely. So comparing on other cloud platforms will be a useful thing to do, and collaborate more closely with the other benchmarking exercises. For example, in ARCHER2, which is kind of its own interesting interconnect, and the Excalibur exascale program in the UK as well, which is just kicking off. So in summary, performance scaling, the single node performance, there was no difference. That was as expected. We expected single node performance to just work. In terms of the multi-node performance, actually the cluster in the cloud behaved just very similar to standard HPC clusters in terms of what the performance looked like. There's some differences in performance, but it's in the right ballpark, and actually most of those will just correspond to tuning, I think, rather than actually fundamentally things that are wrong. We'd like to compare to new HPC interconnect technologies that are used in on-premises systems more, so HDR InfiniBand and the new Clay Slingshot interconnect when we get the chance with those systems available. And the parallel I/O performance on BGFS over ROCE using the local NVMe was very good, and certainly parallel I/O performance has been a challenge in the cloud, I think, for a while. So that was very encouraging. What we learned, well, actually, the gap in expectations and understanding between DiRAC and Oracle was quite large at the start of the project. I think we were expecting something that was closer to what we think of as a standard HPC environment, and Oracle have less experience with what a standard HPC environment would look like and what the expectations and technical skill levels of a typical DiRAC HPC user would be. But throughout the project, one of the best things I enjoyed most was we had a really positive working relationship. Both learned about a lot, learned a lot and understand each other's experience and expectations much better, and what's possible and where the problems are, and what, you know, what's fixable in short term, what takes more time. I think that was one of the major points of this exercise, is we both learned a lot from each other about what was available. Porting was very straightforward once we understood the different environments, and with a few tweaks, as I mentioned earlier, I think actually it could be made even more straightforward, and that barrier could just go away to usage. It would have been nice to have some better documentation on compiling and running the MPI on the bare metal instances, which was mostly actually talk to Oracle and look at the scripts, examine the script source. But again, that's a fixable thing, right? Writing more documentations, a thing that can definitely be done. So that's me at the end of my presentation. I'm happy to stick around, obviously, take questions, comments, and those sorts of things. But thank you for your attention, and I hope you found it interesting as well. Can I say a bit more about the hardware? So the short answer is no, probably not at this moment, but we will be in the technical reports going forward, because I can't reel off the top of my head, essentially, is the problem. I think it's what I said in the talk is what I know in some sense about it on the technical side at the moment. It was BGFS, we used the local NVMe storage, which comes with each of the bare metal HPC instances, and it was configured to run over the RDMA interconnect over converged Ethernet. That is as much detail as I can give. Sorry, unfortunately at the moment, but we can certainly investigate it and get back to you on that. And there will be more details available in the future publications and the technical reports. Okay, if there's no more, don't seem to be any more questions right at the moment. So again, just thank you for coming along, and we'll definitely be reporting more on this sort of thing in the future. So keep an eye out for that. And thank you again.